Hello, welcome to another module in this massive open online course, and we are looking at the concept of duality for optimization. Alright, so let us continue our discussion. And what we have shown is that well, this the dual function, that is the Lagrange dual function GD lambda bar comma nu bar, we have shown that this is concave, correct. And now for a moment let us go to the original optimization problem. Let us go back. The original, possibly not necessarily convex optimization problem, and that is as follows. So, what we are doing is we are minimizing G naught of x bar subject to the constraint Gi x bar less than equal to 0, I equals 1, 2 up to L, and the equality constraint Gj tilde x bar equals 0, J equals 1, 2 up to M. This is our original optimization problem. Now, let P star denote the optimal value of this original optimization problem. Okay, that is, if you perform this optimization, we obtain P star as the optimal value of the objective function, correct, subject to the constraints of this original okay. So, P star, we are denoting by P star the optimal value of the original optimization problem. That is what we obtain as optimal value if you solve this original, possibly non-convex optimization problem. Okay. Now, the interesting result that we want to show is that, and this is the very interesting and very important property of the dual, we want to show that if this vector of Lagrange multipliers associated with the inequality constraints, that is lambda bar, is component wise greater than or equal to 0. That means that each lambda I, right. So, each lambda I is greater than or equal to 0 for I equals 1, 2 up to L. Remember, lambdas are the Lagrange multipliers associated with the inequality constraints. Now, if each lambda is greater than or equal to 0, all right, then the dual, that is GD of lambda bar nu bar, that is always less than or equal to P star, which is basically the optimal value of the original optimization problem, and this is a very important property. This is a very important property of the dual function, which states that the dual function, that is, if the Lagrange multiplier Lagrange multipliers lambda I are greater than or equal to 0, then the dual function GD lambda bar nu bar is always less than or equal to P star, which is the optimal value of the original optimization. And this is a very interesting property. Let us try to understand why this arises. Okay, so let us try to briefly demonstrate this. So, this is a very important property. So, let us try to demonstrate this. So, observe. Now, let's start with the following. Let x tilde be any feasible point. Feasible point means it satisfies a constraint. Satisfies a constraint in the sense that you have Gi of x tilde is less than or equal to 0, I equals 1 up to L, and Gj tilde of text tilde equals 0, J equals 1 up to M. Okay. So, this is a feasible subpoint in the sense that this satisfies the constraints. In the sense that this satisfies the constraints, and therefore, now if you look at the Lagrange dual, if you look at the Lagrangian, correct, L of x tilde lambda bar nu bar. Now remember, you have to keep in mind that lambda bar is component wise greater than or equal to 0, which means that each element lambda I is greater than or equal to 0. So, this is basically, now let me just write it a little bigger so that you can observe this. So, this is G naught x tilde plus summation I equals 1 to L lambda I G I x tilde plus summation j equals 1 to M nu j G j tilde x tilde. Now, what you can observe is, now G naught x tilde plus, now look at this, each lambda I is greater than or equal to 0, x tilde is a feasible point. We have seen that each G I of x tilde is less than or equal to 0, which implies that lambda I, that is if you look at this net quantity, lambda I is greater than or equal to 0, G I of x tilde is less than or equal to 0, implies this lambda I into G I of x tilde is less than or equal to 0. On the other hand, Gj of x tilde equal to 0, we do not care about nu j, Gj of x tilde this is equal to 0, this implies that this whole quantity nu j into Gj of x tilde this is equal to 0. So, we have this is equal to G naught of x tilde plus some quantity that is less than or equal to 0 plus some quantity that is equal to 0, and so you have G naught of x tilde plus some quantity is less than or equal to 0, which is a negative quantity, which implies that this is therefore less than or equal to G naught of x tilde. That is basically your quantity on the left. This is the Lagrangian L of x tilde lambda bar nu bar. This is basically, so this original, this is basically your the Lagrangian for the optimization problem. This is less than or equal to G naught of x tilde for any feasible point. So, this holds for, now remember this holds for any feasible point and as long as all the lambda i's are greater than, that is lambda bar is component wise greater than or equal to 0. Very good. Okay. Alright. So, we have shown that the Lagrangian dual function at any feasible point x tilde, when the vector each lambda is greater than or equal to 0 is always less than or equal to the always less than or equal to G naught of x tilde, that is the value of the objective function at that point x tilde, at that feasible point x tilde. Now, therefore, what we have is G naught of, just rewriting this, G naught of x tilde greater than or equal to the Lagrangian. Okay. Now, G naught of x tilde is greater than or equal to L of I am sorry, the Lagrangian at x tilde, which implies that this is greater than or equal to the minimum over all such feasible points. Okay. So, what you have now shown that G naught of x tilde is greater than or equal to Lagrangian at x tilde, and therefore, you take the minimum of the Lagrangian over the set of all feasible points x tilde. Naturally, G naught of x tilde is going to be greater than or equal to the minimum value on the right hand side, and the minimum value on the right hand side is nothing but the Lagrange dual function. So, therefore, this is basically nothing but this is, once you take the minimum, that is your GD lambda bar nu bar. So, that is basically equal to your GD lambda bar nu bar, and therefore, that implies that your G naught of x tilde is greater than or equal to GD. Okay. So, this is greater than or equal to, correct, this is greater than or equal to GD lambda bar nu bar for any feasible point x tilde. Okay. For any feasible x tilde. Now, naturally, if you take the minimum of this, so for any feasible x tilde, this greater than or equal to GD lambda. So, if you take the minimum of G naught x tilde for the set of all feasible points, this is going to be greater than or equal to, now this holds for any x tilde, correct, this inequality holds for any x tilde. G naught of x tilde is greater than or equal to the dual function lambda bar GD of lambda bar nu bar. Naturally, at the optimal, that is if you take the minimum over the set of all, that is this holds for any feasible point x tilde. So, naturally, it holds for that feasible point x tilde at which the minimum is achieved, correct, that is the minimum over all set of all feasible points x tilde GD of x tilde, G naught of x tilde, that is nothing but P star, which is the optimal value of the original optimization problem. So, this is basically your P star. Which is therefore greater than equal to less than. This is basically nothing but this minimum, this is equal to P star, this is the optimal value of the original optimization problem. This is the optimal value of the original optimization problem. Okay. So, P star is greater than or equal to GD lambda bar nu bar. Okay. Since P star is minimum of, since basically P star is the, since P star equals the minimum of the objective of G naught x tilde over set of all feasible points x tilde. Or the set that contains all the feasible points x tilde, that is what is meant by this, and therefore, you have GD of lambda bar nu bar is less than or equal to P star. Okay. Now, mind you, you have to still keep in mind that this holds true only if lambda bar, that is you also have that, let me just write these things together, for lambda bar greater than or equal to, that is component wise, that is each component of the vector lambda bar greater than or equal to 0, which means that each Lagrange multiplier lambda associated with the inequality constraints is greater than or equal to 0. Okay. So, this is basically that, and therefore, what this shows is GD of this Lagrange dual function for any lambda bar nu bar. So, this holds for any lambda bar nu bar, I mean this holds for any nu bar and any lambda bar such that each lambda is greater than or equal to 0, which means that this Lagrange dual function forms is a lower bound for this P star for any lambda bar greater than or equal to 0, that is component is greater than or equal to 0, and nu bar, this Lagrange dual function is a lower bound for P star. That is, you can say that the optimal value of the original optimization problem is always going to be greater than or equal to the Lagrange dual function. So, this is basically a lower bound. which is basically optimal value of the original lower bound for P star, which is the optimal value of the original optimization problem. Okay. So, for any lambda bar greater than 4, and this is for any nu bar comma lambda bar component wise greater than equal to component wise. Now, naturally, if the Lagrange dual function is lower bound, right, for any lambda bar component wise greater than equal to 0 and nu bar, one can ask the question, what is the best lower bound, right? Because look at this, we have this P star, we have this concave function which is GD of lambda bar nu bar. Alright, this is always lower than P star. One can ask the question, what is the best lower bound? What is the best lower? The best lower bound is the maximum value of this lower bound, which means we want to be as close as possible to the optimal value P star, because if you look at it technically, if you look at the lower bound of minus infinity, that is always going to be lower bound, right? Any P star is always going to, but we want the best possible lower bound. What is the lower bound? Which is as close as possible to the P star, so that this gap between the lower bound and P star is minimized. So, gap between lower bound and P star is minimum, okay, and that is basically given as the maximum value of the Lagrange dual function GD, of course subject to the constraint now that lambda bar is component wise greater than or equal to 0. And now you can see that this is an optimization problem, this is also an optimization, the best lower bound is also an optimization problem, finding best lower bound and in fact the interesting thing about this is a convex optimization problem. Although the original problem need not be convex because this is concave. So, I can equivalently write this as minimum of GD minus GD lambda bar. So, GD lambda bar nu bar is concave, minus GD lambda bar nu bar is convex. I can, instead of maximizing GD lambda bar nu bar, I can minimize minus GD lambda bar nu bar, subject to the same constraint lambda bar is greater than equal to 0. In fact, I can put a negative sign here and I can make this reverse, minus lambda bar is less than or equal to 0, and this is your standard form convex. So, you can use all the techniques of convex optimization to conveniently solve the dual problem. This is known as the dual problem, where you are optimizing the Lagrange. So, this is basically the interesting dual problem. The original problem is termed as the primal problem. Primal and dual. So, even if the primal problem is non-convex, the dual, the equivalent dual problem that is derived from the primal problem is convex, and therefore, one can conveniently use all the techniques of convex optimization to solve the Lagrange dual problem. So, primal problem is a dual problem is convex. Even if primal problem is non-convex, okay, which implies one can conveniently solve the dual problem using tools of convex optimization. Convex optimization tools or convex optimization solvers and so on. So, one can use all the tools and techniques for convex optimization available for convex optimization to conveniently solve the dual problem. And remember, because you are taking the best lower bound, that is going to give you something that is as close as possible, the best lower bound, there is a lower bound that is as close as possible to the optimal value P star, but still it is going to be always lower than P star. So, what you get by solving the dual optimization problem is always going to be a lower bound, you are going to get the best lower bound, but still it is a lower bound, it is lower than P star. Okay. Now, when is it equal to P star? Okay. Now, it is always going to be, because remember, so this is GD lambda bar nu bar is less than or equal to P star, okay, for all lambda bar greater than equal to. So, if you take the maximum of this, remember this holds true for any lambda bar nu bar, okay. So, at the maximum also, which holds for some particular lambda bar nu bar, this is going to be less than or equal to P star. So, implies if you take the maximum, right. So, for any lambda bar nu bar is less than or equal to P star. So, if you take the maximum of this for some optimal value of lambda bar nu bar, this is still going to be less than or equal to P star, okay. And therefore, this lower bound, now if you call this dual optimization problem, if the optimal value of this is D star, so D star is always going to be less than or equal to P star, okay. So, D star is the optimal value of the D star is the optimal value of dual optimization problem, P star equals optimal value of the primal problem. This is the optimal value of the primal problem, and this is basically your D star, okay. This is basically where the D star, which is the maximum value of the Lagrange dual function, okay. And this gap now that you see between D star and P star, that is your duality gap. So, D star is less than or equal to P star, and this gap P star minus D star, this is your duality, this is termed as the duality gap. Now, if P star equals D star, that implies P star minus D star equal to 0, that implies duality gap equals 0. Now, when this happens, it is said that strong duality holds. So, this implies that strong duality holds for the problem. Otherwise, if D star is less than or equal to P star, this is simply weak duality. This is simply weak duality, this always holds. In the special case that P star equal to D star, that is, if you look at this, the primal problem, this is convex, okay. So, this is your primal problem, which is convex, and this is the optimal point, which is P star, which is the optimal value of the primal problem. and then you have the dual which is concave, and you have the optimal value of the dual problem which is, so the primal problem is convex and you have the dual problem, or you have the which is concave. Okay, this is equals optimal value of primal problem this is optimal value of dual problem. Okay, and when P star equal to D star, when this D star equal to P star, this implies that basically your duality gap is 0. Implies strong duality holds. This implies that strong duality holds. When duality gap is 0, strong duality holds for the problem, and this is typically true. Loosely speaking, the strong duality holds for any convex object, although this does not hold. Although one can form the dual optimization problem, solve the dual optimization problem for any and possibly non-convex problem, but strong duality typically holds only for a convex optimization problem. So, one can either solve the primal problem so this typically holds only for a convex optimization problem, right. So, that is the theory of duality. So, you have the primal problem, optimization problem from the Lagrangian dual function, alright. You form the Lagrangian, take the infimum or minimum with respect to x, you get the dual, the Lagrange dual function, alright. You can take the, which is always a lower bound for P star, which is the optimal value of the original problem. What is the best lower bound? You maximize the Lagrange dual function subject to the constraint that lambda bar is component wise greater than or equal to 0. That will give you D star, which is the optimal value of the dual optimization problem. Now, D star is always less than or equal to P star. If D star equals P star, then we say that the duality gap is 0, strong duality holds, and this is typically true for a convex optimization. And often solving the dual is either easier, or solving the dual problem yields valuable insights into the original optimization problem itself. So, it is always a good exercise to have the primal problem, and even if you are able to solve the primal problem, it is always a useful exercise to construct the dual optimization problem, solve that, see if the solutions to these two match, and then see what insights the dual optimization problem offers. So, the primal and dual, they always go hand in hand for any optimization problem, in particular for a convex optimization problem, because the duality gap is 0. So, we will stop here and continue in the subsequent modules. Thank you very much.